Hello students, today we will discuss the motion of center of mass. As we have known earlier that what is the center of mass? It is a point where the complete mass of the object can be considered to be concentrated. When an object is in motion, its complete body structure having number of particles by which it is composed of are also moving. So we can also say the center of mass is also moving with the motion of the body or the object. Now we will discuss how the motion of the center of mass is concerned with different physical quantities, say velocity and acceleration, and the change in the position of the object. So we are taking our today's topic, motion of center of mass. We know that the position vector of a center of mass we represents by a vector capital R, which is equals to sigma mi ri vector divided by sigma mi. Sigma mi is also considered as the complete mass of the system, or combined mass of all the particles of that system. In that case, we can also write the same equation as m r vector equals to sigma mi ri vector. So here, do remember r is the position vector of center of mass of the system or body with respect to origin, and m equals to sigma mi, which is complete mass of the body or the system. Now, if we take here the equation mr equals to sigma miri as equation number 1, the same equation we can represent by mr equals to m1 r1 vector, m2 r2 vector, and up to mn rn vector, where we are considering that system has n number of mass particles. Again, this is the same equation, equation number 1. Now see, if we differentiate the equation number 1 with respect to time, then we will get another term. What it is? M dr upon dt equals to m1 dr1 upon dt plus m2 dr2 upon dt plus up to the nth term mn drn upon dt. As we know, the r expresses the position of the center of mass with respect to origin, and if the position of that center of mass changes with respect to time, it means the term dr by dt will be the velocity of the center of mass. Similarly, the term dr1 by dt, dr2 by dt, these all terms will be the corresponding velocities of the mass particles, or you can say the change in their position with respect to the origin. So the same equation we can write here, m v, v for velocity of the center of mass, will be equals to m1 v1 plus m2 v2 plus mn vn. It means the momentum of the center of mass will be the vector sum of the momentum of the each mass particle of the system. For that, we can consider it the equation number 2. Now see, if we again differentiate the equation number 2 with respect to time, then it will uh, notify the term rate of change of velocity. It means change in velocity with respect to time. We call it acceleration. So again the same equation on differentiating m dv by dt will be equals to m1 dv1 by dt plus m2 dv2 by dt up to nth mass particle mn dvn by dt, which can be further rewritten as m capital A denoting the acceleration of the center of mass, m1 a1 denoting acceleration of the mass particle 1 plus m2 a2 denoting acceleration of the mass particle m2 and up to the mass particle mn. Say this the equation number 3. Since we know, according to Newton's second law of motion, the force on a mass or mass particle is given by mass multiply its acceleration. So here in equation number 3, it can be termed as where capital MA can be represented as force on that complete system and M1A1, M2A2 and so on can be considered the force on individual mass particles. So the same equation number 3 can be expressed in terms of force which is acting on that system or the body comprising n number of mass particles. So we can write the equation 3 can be expressed as a force acting on a system of n and number of mass particles. That means we can write the equation as force acting on the center of mass can be considered as the vector sum of the forces acting on different mass particles. And we can also say if the different forces are acting on each of the mass particle of that system, then their vector sum will provide the force acting on the center of mass of that system. Here remember one thing, that the forces acting on the body may be the internal forces acting inside the body and may be the external forces acting from the outside region of the body but acting on the body. Since according to Newton, all the internal forces within a system are balanced with each other, so we don't take their consideration in our calculation. But since the external force can change the direction or the position of the object, so they would have to be taken into consideration. That's why here we will consider all the external forces acting on the mass particle from which the system is composed of, and all the vector sum of the forces applied on mass particles can be treated as it is a combined force capital F acting on the center of mass of that system. So from equation 3 we get m multiply acceleration is equals to F external applied on that body or system of particles having n number of particles in it. Thus we can say that the center of mass of a system of particles as if the complete mass of the system is concentrated on it, and all the external forces all the external forces are applied at that point, means the center of mass. So I think it is clear to you that if a body or object is in motion and it is composed of a number of particles having different masses or the same masses, in that case the motion of the complete system can be considered in terms of its motion of center of mass, where all of the mass can be considered to be concentrated on that point which is known as center of mass, and all the forces, external forces, which are acting on the body in various directions can be considered as they are acting at the point center of mass. That's why the center of mass is moving due to or under the effect of different external forces. To completely understand this thing, we can consider an example of a projectile motion of a bomb. Suppose a bomb is thrown at some angle with respect to horizon with some velocity, and it executes a projectile motion. In that case, meanwhile, in its journey, at any time instant, when the bomb explodes, all the mass particles of the bomb is scattered and do their individual motions in different directions. Definitely it is a projectile motion for each mass particle which has been scattered from the bomb. But since the center of mass of the bomb was already in the motion along the projectile path of the bomb when it was not exploded, so its complete motion after the explosion of the bomb during its journey, the center of mass will follow the same path of the projectile motion as it could follow if the bomb were not exploded. So its position is changing as it could change if the bomb did not explode. So that's all for today. We will continue in the next turn with next topic. Till then, good day.